Hello friends. So, one second. Okay. So today we are going to discuss 3 questions, and all these 3 questions are from statics. And the first question, okay. So in the first question, it is asked that an Atwood machine shown consists of n masses with the values m, m by 2, m by 4 up till m divided by 2 raised to power n minus 1. All pulleys are massless and strings are also massless. So based on this, we have 2 questions. Attach a mass of m 2 raised to power n by n minus 2 to the free end of the bottom string. Determine the acceleration of all the masses. Now remove the masses m 2 raised to power n minus 1, which is arbitrarily small, to the larger value of n. What is the acceleration of all the masses after this infinitesimal mass is removed? So we are given an infinite chain of the Atwood machine. Okay, so we can just draw the approximate figure. So this is our first pulley, and to this first pulley on the left side a mass m is attached, and to the right side of it there is another pulley, and then to this another pulley a mass on the left side m by 2 is attached, and to the right end of this thread we have another pulley, and this is a basically continuous process. So you can see this goes on increasing, and finally at the end we are having another pulley, and to the right of it a mass of m by 2 n minus 1 is attached, and to the right side of this thread is the mass whose value is going to change according to part A as well as part B. Okay. In part A, on the right side, same mass is being attached, and then this mass is being removed. Okay, so we have to find out the acceleration based on this. Okay. So first of all, this we try to write the formula for an Atwood machine in which we are having only 2 masses. Okay. So this is the basic Atwood machine, and suppose on the left side we are having a mass A, and on the right side we are having a mass of B. And we assume that our mass A is moving in upward with the acceleration of A, so obviously mass B is moving downward with the acceleration of A. And based on this we can find out the value of the tension in the string. Let us suppose that tension is about T, and we can also write the equation for our acceleration. So in general we can write that our acceleration equation it can be written as our B minus A divided by our A plus B. Okay, and this is when A is moving upward. If A is moving downward, B is upward, so sign is going to reverse. Okay, and then we can further write the value of the equation for our tension also. Okay, and we can say that our tension T will be equal to, sorry, it is being multiplied by G, and tension T, it can be written as our 2AB divided by our A plus B times G. Okay. Now this we can apply to this all continuous chain, or we can say a tree format. Okay. Therefore, let's assume we are going to first of all derive the general equation for all this tree setup given to us, and based on this we can just put the values in the final and get the answer. Okay. So we assume that our mass A is equal to our m of k, and our B is our mu k plus 1. Okay, and we have to remember that this mu k plus 1 is equivalent mass of the entire subtree. Okay, subtree is nothing but this part. Okay, so this is the equivalent of our mu plus 1, mu k plus 1. So we can say that our mu k plus 1 is equivalent mass of the entire lower subtree. So if the equivalent mass is mu k plus 1, therefore from here we can write that the force with which this subtree will be pulled downward will be mu k plus 1 times G. Okay, therefore we can say that the weight of subtree, mu k plus 1 times G, is the weight of the subtree. And based on this we can find out our tension. Okay. And here we have, okay, let me write this as small, okay, because this here was small t, and here also we have tension small t, and capital T we are going to assume this is the tension with respect to the pulley. Therefore, we can put our A is equal to m of k and mu is equal to k plus 1 in our equation for our tension. Therefore, we can say tension Tk will be equal to twice m of k mu k plus 1, and this comes as m of k plus mu k plus 1 times G. And so basically what we did, we assumed a kth state, and to one end of it, that is our right side, we assumed that the weight is our mk of k, and to the right side, because of the subtree, we assume that this mass is our mu k plus 1, and respective tension in the each side is our T, and capital T is the total tension of the pulley part. Okay. Therefore, we can say that our capital T of K will be obviously equal to twice Tk, which gives us 4 mk, and this is mu k plus 1 mk plus mu k plus 1 times g. And we can also say that our one second. Okay, so now we have our two cases, okay, and in general, let me write that the various formulae which we just derived. Okay, so we derived that the tension our in individual string, that is our T of k, is our twice mk k minus 1 divided by mk and mu k plus 1, and tension in the main thread which is connected to the pulley axle is T of k, which is nothing but our twice T of k. So this will be coming as our 4 mk mu k plus 1, and this comes as mk plus mu k plus 1. And we can also write that our mu of k will be equal to 4 mk, and this comes as mu k plus 1, and this comes m of k plus mu k plus 1. And we can write our acceleration also, and acceleration comes as our mu k plus 1 minus m of k, and this comes over m of k plus mu k plus 1 times g. And also we can say that let's say that we are having n masses, and there are n masses, and these masses suppose are represented as m1, m2, m3, and so on up till mn. And we can also write that our, if you make with respect to pulley 1:1 comparison, our m1 will be equal to our m, m2 will be equal to our m by 2, m3 will be equal to our m by 4, and so on, and mn will be equal to our m, and this comes as 2 raised to power n minus 1. And also in general we can write that our m of k will be equal to our m 2 k minus 1, and where k varies from 1 to up till capital N. Now we have two you can say cases that so we have a part A. In part A, let us suppose it is given that we are attaching a mass m of n which is equivalent to our m minus this function. Okay, so for the sake of simplicity we can say that let we have a mass s which is equal to our m to n. And in part B, it is given that this mass is removed, so it means value of S is equal to 0. So okay, this is going to solve our question comparatively easily. Okay, and so we can, let's define that we are having a, let us suppose we are having a, suppose this is our kth state, okay, and to this we have attached a pulley, and here tension is given as T of K, and on the left of it we are having a mass, okay, and suppose that is our M of K, and on the right of it obviously there will be a pulley, so we are having a tension here small T of K, and same as our here also T of K, and just below it, and suppose this is our mu K plus 1, and so here we can further extend it, and there will be here another pulley, and to the left of it we are going to have a mass K minus 1, okay, and one second, yeah, and therefore we can, on the right side of it, once again this is our state, and let us suppose we call this as mu of K, and once again we are going to have a pulley will be there, and on the right of it, left of it, we are going to have mass Mk minus 2, and this will be going on continuously. Okay, so this is basically a chain or like a tree. Okay. Therefore, from this we can say that we have our mu of K, and it is our effective so let us say that at level K, like you said, we are having T of K is our tension in each two ropes, and below the pulley with a pulley that connects mass M of K, mass M of K to the subtree mu K plus 1. And for the tension, we already know that our T of K is equal to twice small T of K. And so we can write that the effective mass recurrence, it can be written as our, because we have a mu of K, and for our kth that is multiplied by G, and that will be equal to capital T of K. and mu of k we have already written, or we can just write from here also. So we can write the mu of k is equal to 4 times m of k, mu of k plus 1, and this comes as our m of k plus mu k plus 1. This is nothing but a recurrence relationship. And so let us consider our option number 1, that value of s is equal to mn. Option number part A. So we have our part A, and part A we have assumed that our s is equal to our mn. Okay. And therefore, because it is our lowest level, okay, and on the left side we are having already our m of n, and on the right side we have connected a s, and the value of s is equal to our m of n. Therefore we can say for the lowest we are having a left mass which is our m of n, and we are having our right mass which we have denoted as s, and that is also equal to our m of n. So it means value of A is equal to m of n, and value of B is equal to also our m of n. So they are same. Therefore we can easily write our tension T, because general formula we have already written for tension T, and that tension T is equal to, this is our A mass and this is B mass, and A plus B. Okay. So we simply substitute here m of n in both sides. So we get tension T, that is our T of n. It can be written as 2 m of n times m of n divided by m of n plus m of n multiplied by g, and this gives us m of n times g. Okay. And so this is our tension T, and we can also write that we can just generalize the entire equation, and we know that our mu of k, mu of k we have already written, so you can say our mu of k is equal to 4 times m of n multiplied by m of n, and this comes as m of n plus m of n, and this gives us square, and it will be coming as our twice m of n. And so let me put it here. We have our T of n is equal to our m of n times g, and we have our mu of k is also equal to twice of m of n. Okay. Therefore we can generalize this formula, that this will be, so here it is n not k, mu of n. So this will be our n. So we can generalize this formula for any stage, that mu of k is equal to twice of our m of k. And similarly we can also write that mu of k plus 1 will be equal to twice of m k plus 1. This we can easily generalize for every value of k. And So finally we can use our equation for our acceleration. So we know that our acceleration is given as our m of k minus mu k plus 1, and we have our m of k plus mu k plus 1. Okay. And here we have already know the relation that our mu of n is equal to twice m of n, and we have our mu of k is equal to twice m of k, and therefore we can write that our so we are given that our m of n is equal to our m of 2 raised to power n minus 1. Therefore we can write for it any value of k is equal to m of 2 raised to power k minus 1. And if we can mathematically write it as our twice m divided by 2 raised to power k, and if I substitute this as a m of k plus 1, then m of k plus 1 will be equal to m 2 raised to power k. It means in place of this m 2 raised to power k, I can simply write m of k plus 1. Therefore I get from here that m of k is equal to our m of k plus 1, twice m of k of plus 1. So this relationship we are going to use. Okay. And we are going to use this particular equation. So let me write it here once again. So we have a acceleration is equal to our m of k minus mu k plus 1 m of k plus mu k plus 1 times g, and we substitute it, we get this as our m of k minus twice m of k plus 1 divided by m of k plus twice m of k plus 1. And we know that our m of k is nothing but our twice m of k plus 1. So we get this twice m k plus 1 minus twice m k plus 1 divided by twice m k plus 1 plus twice m k plus 1. Therefore we get that our acceleration is equal to 0 for all values of k. So it means all the masses are in equilibrium as the acceleration is equal to 0. So we can say our all masses are in equilibrium. Okay. And now the part B states that our bottom mass is removed, that is S is equal to 0. So we have a part B and bottom mass is removed, that is S is equal to 0. Okay. So if S is equal to 0, so basically means that on the left side we are having mass our m of n, and on the right there is no mass, that the value of mass is equal to 0. Therefore from here we can write our tension T of n will be equal to twice m of n times 0, and this comes as m of n plus 0. So this gives that tension is equal to 0. Therefore we can write our mu of n will also equal to 0, and this will be reoccurring in the upward direction, or we can say for our mu of k at any position will be equal to 4 m of k times 0, and we have m of k plus 0 which is equal to 0. So it means we have our v of k is equal to 0 for all values of k. And if we have our for all values of k, therefore we can write, 1 second. So we have our v of k is equal to 0. Therefore, we can say that our acceleration, that is our a of k, will be also equal to our m of k minus 0 will be equal to m of k plus 0 times g is equal to 0. So it means, sorry, not 0 but g. Therefore, we can say that every mass is having acceleration of a of k is equal to g, which is nothing but our free fall. So in the first case, everything will be in equilibrium, and the second case, every mass there will be a free fall. So we come to the next question, and in this next question it is said that it consists of 3 pulleys, a short piece of string connecting one mass to the bottom pulley, and a continuous long string that wraps twice around the lower side of the bottom pulley and once around the upper side of each of the 2 pulleys. The 2 masses are m and 2m. Assume that segment of the long string connecting the pulleys remains essentially vertical. Find the acceleration of 2 masses. So this is diagram is a little bit typical, otherwise question is quite easy to solve. Okay. So we have, suppose this is the fixed portion, and to which we have a pulley. So let us suppose this is our first pulley. We call this as pulley A, and then we are having a second pulley, and let us suppose we call this as pulley B. 1 second, let me draw it. And we are having a string which is wrapped around pulley A, and then it goes around pulley B, and suppose this is pulley C, and it goes upward around pulley B and then comes back to pulley C. Okay, and then it goes and it is connected to the vertical fixed portion. Okay. So the string starts from here, moves in this direction, and then it goes once around, and this is fixed, this is pulley B, and then it from this pulley C it is wound twice and then goes back to the fixed position. Okay, this is the basic configuration of the question. And this mass A is having a mass m connected, and pulley C is having a mass of 2m connected. Okay, and we are supposed to find out what will be its acceleration. Okay. And first of all, we have to find out the constraint relationship. So let us assume that our mass m is moving in upward direction with the velocity of v of a, and this 2m is moving in upward direction with the velocity of v of c. And obviously the string is same, so tension T will be same in all the segments. So this will be tension T, T as well as T. Okay. Direction will be like this. Therefore, we can write that we can write the equation. So we can say for constraint relationship, or constraint relation, we can write that our tension T multiplied by V of A plus, and for C we are having 4 tensions, so this comes as 4 of T multiplied by V of C is equal to 0. Therefore, we can write that our this V of A is equal to minus 4 V of C, or we can write our acceleration of A is equal to minus 4 times acceleration of C, and this is capital. Okay, so this is the constraint relationship between these tensions. Okay, and so for now we can just segregate for individual masses. Okay. Therefore, we can say for our pulley A or mass M. Therefore, we can write that let me dot this pulley A. So this is pulley A, and on the left of it we are having a mass M, and tension T is upward direction, so this is pulley A. Okay. Therefore, we can write for mass M, we can say that our, one second, okay, so let me write this equation in terms of the mass. So this is our acceleration of mass M minus 4 times acceleration of mass of 2m. Okay, not in terms of the pulley, much more easier. And therefore, if it is having acceleration upward in our this A of m, therefore we can write the equation of T minus mg is equal to our m times A of m. Okay. And similarly, we can write for mass 2m, and 2m is connected to our C. So this is pulley C, and let us suppose here tension is given as our S, and this is our 2m, and therefore, and here also let us assume it is moving in upward direction. Okay. And its acceleration is acceleration of 2m. Therefore, we can write the equation, and that equation will be equal to our S minus 2m g is equal to our 2m times acceleration of our 2m. And this pulley C is connected with the 4 strings, something like this, and all these strings are having a tension of T. So T, T and T. Therefore, we can write that for, so from here we can say that our 4T minus S will be equal to 0, or we can say our S is equal to 4 times T. Therefore, we can, let us put this over equation number 1, and this is equation number 2, and this is equation number 3. So we can say from 2 and 3, from equation 2 and 3, we can write this as over 40, and so we can write this as over 40 minus twice m g is equal to over twice m acceleration of our 2 mass, 2m. Okay. And so we can say that our dimension T will be equal to, we can just cancel out twice throughout, and we get that tension 2T will be equal to, we have this as our m, a of twice m plus m of g. Okay. And from our equation number 1, we can write from here that tension T is equal to our m of a of m plus m of g. Therefore, and moreover, we can use the constraint relationship and substitute our a of m. Okay, so we can say that our a of m is equal to minus 4 a of twice m. Therefore, we get that our, let me call this as equation number 1. So you can say from equation 1, we get our tension T is equal to over m minus 4a twice of m plus mg. And this gives us that tension T is equal to our mg minus 4m and a twice of m. And we already know value of our tension T. Therefore, this is our third, this is our fourth equation, this is our fifth equation. So we can say from equation 4 and 5, from equation 4 and 5, we can write that our twice mg minus 4m 2 of m is equal to m a twice of m plus twice mg. One second. Not twice, but mg. Yeah. And now it is simple. From here, we can calculate our a of m, and let me write it directly. So therefore, we can say that a of 2m will be equal to our g by 9, and we know that our a of m is equal to minus 4 times a of 2m, so this comes as g upon 9. Okay, so here this a of 2m rather will be moving in upward direction, so this is our upward, and a of m will be moving in the downward direction because the sign is negative, so this will be moving in downward direction. So these two are the acceleration of respective masses. Next question. So it states that consider the Atwood machine shown in the figure containing two masses m. The system is placed on the frictionless plane, inclined at an angle 30. Find the acceleration of the two masses. So figure is given, and we are given that we inclined plane, and the inclined plane is at angle of 30 degree, on which we are having a mass m, and it is connected with a string, and that string goes around a pulley. And then it goes once also around the pulley, and here we also have another pulley, and through which it connects with the axle here. Okay, so these two are fixed. So this is our basic figure given to us, and let us suppose we have this our A and B and C, and to this B a mass m is attached, and here it is also mass m. Okay. So this is our basic figure given to us, and now we can, first of all, let's find out the constraint relationship between the acceleration of two masses. Okay. And let us assume it is moving in the direction of, let us suppose this is our Vp, the velocity along the plane, and this is our Vb. Okay. The string is same, so the tension will be T all along same. So we are going to have tension T that will be same for the entire string. So we can write that the constraint relationship for the constraint relation, we can write that our T times V of P and plus, let us assume, and we are having 1, 2, 3. So this is our 1, 2 and 3. So we can say this is our 3 times T, V of B is equal to 0. Okay. And so we can write that our this V of P is equal to minus of our thrice V of P, or acceleration, we can say acceleration of the mass on the plane will be equal to minus thrice times acceleration of our B. So this is the constraint relationship between the accelerations. Okay. And now we can just solve the question based on the, you can say, the equation of our this, and moreover it is given in the question that, okay, it's frictionless, so it doesn't matter. Okay. And so for our pulley B, let me draw it broadly, and the first, so this is having a tension T, this is our extreme, this is our tension T, and the final one is connected to our axle, and it will be in the downward direction, and this is with respect to pulley B, and this is connected to a mass m, and let us suppose it is having a tension of S. And therefore we can write that for pulley B, we can say that we have our two tension upward direction, therefore we get this as our 2T, and we are having S and T, this and S in the downward direction with respect to pulley B. So we can say this is minus S plus T is equal to 0. And from here we can say that our S is equal to nothing but our T. Now we come to our hanging mass, and for the sake of, let us suppose we call this as our M of B. Later on we can just substitute our values, and therefore we can say for hanging mass M of B, we can write that our, if it is moving in the upward direction, okay, with the acceleration of A of B, therefore we can write the equation as our S minus MB of G is equal to our this comes as A of B times M of B. Okay, now we can substitute M of B as our M. Therefore we can say that our S is equal to, we can write it will be equal to our A of B times M plus M times G. So this is equation number 1. Okay. And now we come to the block on the plane. So we can say that our block on the plane, and this is an inclined plane at an angle of over 30, and we have our, this is mass M, and for the sake of convenience let us call this as our M of A or M of P plane. Okay, so let us call this as our M of P, and we are going to have a tension T. So we are going to have here MP of G, which we can divide into two components. This will be over 30, and we are having our MPG cos of over 30, and this is our MPG sine of 30. It is moving upward with the acceleration of A of P. Therefore we can write the equation, and that equation will be our tension T minus M of P G sine of 30 is equal to our M of P multiplied by A of P, and M of P is nothing but our M. Therefore we can write our tension T minus our M G, and this comes as divided by 2 is equal to M A of P. Okay, so this is our equation number 2. And we already know the constraint relationship, that acceleration of the plane is equal to minus of acceleration of our B. Okay. Therefore we can write that our, this equation number 2, we can further write it as our A of P. So this comes as a T minus mg by 2 is equal to M, and A of P is our minus thrice acceleration of our B. And therefore we can say that our tension T is equal to, we get this is our mg by 2, and this is minus thrice M A of P. But we know that our S is equal to T. We have already proved this relationship. Okay. Therefore we can say that our, and another, so from equation 1, so you can say from equation 1, let me write it here. From equation 1 we are having that our S is equal to A of M, A of B times M plus mg. But we know that our S is equal to T. Therefore, we can say that our T is equal to our A of M, A of B times M plus mg. Now, we have, this is our first equation of T and this is our second equation of T. So we can just interchange them, and we have already equation 2. So this is equation number 3 and this is equation number 4. So we can say from equation 3 and 4, from equation 3 and 4, I can write is equal to our ABM plus mg is equal to mg by 2 minus 3m A of B. And now it's quite simple. Mass is not required, and we get our acceleration. And we can get this as a 4A of B, and 4A of B will be equal to, this will be g by 2 minus g. Okay, so we get this as a 4A of B is equal to our minus g upon 2, and therefore we can say that our A of B is equal to our minus 1 by 8 times g. So it means it is moving in downward direction. Okay, because we have taken initially that it is moving upward, so obviously downward. Now we can easily find out our A of P. We know that our A of P is equal to minus of our thrice A of B, so this comes as plus 8 times g. So it is moving along the plane, okay, or we can say up the plane. Up the plane. And if required, we can find out a tension. In the question it was not mentioned, but that is sometimes quite possible. So we can say tension T, because we have both value of acceleration this, so this comes as minus 3 of m, and this comes minus g upon 8 plus 1 by 2 mg. So this comes as 7 by 8 times mg. So this was our second question, and we come to our, oh, we have done third questions. 1 second, yeah. So this was the third question, sorry. So these were the 3 questions for today, and these 3 questions were of our Atwood machine, or we can say pulley mass combination. So this completes 3 questions.